What is the buoyant force on a volume in a fluid like water? So I've got this picture here that is meant to be of an arbitrary piece of water. So maybe a box-like shaped region in the water somewhere. And it's showing the pressure forces on it. Since pressure forces increase with depth, the length of these arrows have increased the further down that you go. But they're always going to point at right angles to sort of the arbitrary borderline that I've drawn to describe my arbitrary piece of water. So we can analyze that. We can analyze those forces to come up with the correct overall expression for the buoyant force. So let me kind of redraw that box. And I might simplify some things a little bit because that drawing is meant to show a little bit realistically, because really pressure forces are distributed over an area and would be kind of continuously distributed. But maybe I can simplify this to just 4 forces. So there'd be a force down here, a pressure force. There'd be a smaller pressure force on top, and there'd be the 2 pressure forces on the side. Now we know that those 2 pressure forces on the side would cancel each other out, but maybe to find out what the total buoyant force, I'm going to claim that the buoyant force is really there because of these pressure forces. And in that sense, I think if I label this upper pressure force as force number 1 and this lower pressure force as force number 2, then I would say the net buoyant force would be equal to F2 minus F1. And again, I'm ignoring the side forces because they cancel out. But the force F2 is really corresponding to whatever pressure is at the bottom. So I'll call that P2 times the area on the bottom of this arbitrary piece of water, minus the pressure on the top times the area of this arbitrary piece of water. So I'm thinking the area I'm describing is really the area of the top and the bottom respectively, which, if this is a good box shape, should be the same. Based on the formula for pressure as a function of depth in water, which there would be like atmospheric pressure, right, plus rho GH was what we said. So for P2, there'd be a rho GH2, and that would still be multiplied by area, minus the quantity of P naught plus rho GH1 times that area. But what's going to happen here is P naught A here will cancel the minus P naught A in the second one. And so the overall result we're going to get is we're going to have rho GH2A minus rho GH1A, which could maybe be rewritten as rho GA times H2 minus H1, where these H's really represent the 2 depths, right? H2 was the lower depth or the higher depth. It would be a larger numerical value for that, right, in some unit of length, maybe meters. And then H1 would correspond to the depth at the top here. But maybe I could rewrite this simply as rho G A delta H. And that delta H would really represent just the height of the arbitrary box of water that I've drawn. So that's what I think delta H is right there. And if that's delta H and A is the area of kind of the horizontal cross section of the box, then I think that is equal to rho G times volume. And rho really here was the density of water. So rho times volume is the mass of water times G is really equal to the weight of fluid displaced. However, this form of the formula right here, I think that's the one that we saw on the key concepts page. It actually had a subscript of rho fluid, but I've left that off here. V, I think, was volume displaced, which in this case is equal to the volume of this box. For a floating object, it may be different. So that formula for appropriate values works for pretty much any situation involving the buoyant force. The ones based on specific gravity were more specific to certain situations. But that's what we're going for right there, is basically that rho GV. And you can see that in a very similar way, that's the answer that's presented to us in this slide.